Hi everyone, how can you prove that a function is even, or odd, or neither? Or what if you don't know? Here we have a rule for f of x. Now, if you wanted to do an even-odd analysis, what should you consider? F of what? F of what? We want to consider opposite inputs. We want to know what happens if we input opposite values into the function. So we consider f of opposite of x, and we consider what S word. We perform what S word? A substitution. We substitute x with the opposite of x. Make sure to put grouping symbols. So f of opposite x is 3 times the opposite of x, that's to the 4th power, minus 7 times the opposite of x, that's to the 2nd power, plus 1. But wait a minute. What impact do the 4 and the 2 have on these negative signs or opposite signs in here? Well, the 4th power of negative 1 is positive 1. The 2nd power of negative 1 is positive 1. Basically, these signs are destroyed by the even integer exponents. So we're basically left with 3x to the 4th minus 7x squared. We can ignore these in here. We have 3x to the 4th minus 7x squared plus 1. And we get the same rule as before. 3x to the 4th minus 7x squared plus 1. What happened? When we substitute x with its opposite, well, the even exponent just killed these negative 1 factors in here, and the plus 1 out here didn't care. It wasn't impacted by this at all. It just stayed out there. So f of opposite x equals f of x. This is true for all real values of x, which was the domain of the function, and r is symmetric about 0. Remember, for an even function, we need the domain to be symmetric about 0. The same goes for odd functions. Therefore, the function is even. QED, end of proof. Now, how can we prove that this function here is odd? F, where f of x equals 4x to the 5th plus x to the 1st. Well, again, we consider f of opposite x. We consider opposite inputs. Again, we think of what S word? We substitute. Again, we substitute. We're substituting x with its opposite, the opposite of x. So we have 4 times the 5th power of opposite x plus opposite x. This time, however, unlike before, what happens? These guys pop out. The 5th power of negative 1x is negative 1x to the 5th. And then negative 1 times 4 is negative 4. So basically, the negative sign here does pop out and changes the sign here from a positive 4 to a negative 4. We're going to see that odd functions tend to do that. Over here, once again, this opposite sign, this negative 1 factor pops out, and we end up with negative 1x over here. The plus sign basically flips to a minus sign. So we get here negative 4x to the 5th minus x, which is the opposite of 4x to the 5th plus x. It's the opposite of this original expression over here. So f of opposite x is the opposite of f of x for all x in the reals. R is the domain of the function. R is symmetric about 0. Therefore, we have an odd function. QED, end of proof. Bear in mind, if we had had a plus 1 out here, then this would have been messed up because there's no opportunity for the plus sign to become a minus sign. This helps explain why if you add a 1, a 2, or a 3 or something, you destroy the odd property. Speaking of which, what about this neither function here? G, where g of t equals t cubed plus t plus 1. Well, there are a couple ways you can approach this. One way is to do what we've done before. Substitute or replace t with its opposite. So consider g of opposite of t. Right? Replace t with its opposite. We get the cube of opposite t plus 1. We get this over here. And here's the thing. Is this even, odd, or neither? Could this be an even function? Is this equivalent to this over here? Is g of opposite t equivalent to g of t? Doesn't look like it. G is not even because g of opposite t is not equivalent to g of t on the domain. Could this be an odd function? Well, does it look like this is the opposite of this over here? Well, we have a minus sign and a minus sign, but the plus 1 stays a plus 1. Okay. Similarly to what I discussed before, the plus 1 had no opportunity to flip sign. So g is not odd because g of opposite t is not the opposite of g of t either on the reals. So that means that g is neither. But here I'm kind of going by looks. I'm saying that this over here doesn't look like it's equivalent to or the opposite of the original. To be a bit more precise, we should consider a counterexample. For example, what happens if we plug in t equals 1 and t equals negative 1? So let's consider g of negative 1 and g of positive 1. G of negative 1 is negative 1. G of positive 1 is positive 3. Right here, I know that g is neither. G is neither even nor odd. And how do I know that? Just from this counterexample. Well, here's the thing. If g were an even function, if g were even, then g of negative 1 should equal g of 1. But negative 1 does not equal 3. The outputs are not equal. So opposing inputs do not yield equal outputs, therefore g cannot be even. Likewise, if g were odd, then g of negative 1, remember the domain is all reals, g of negative 1 should be the opposite of g of 1. But wait, negative 1 and 3 are not opposites either. Opposing inputs yield outputs that are neither equal nor opposites. If they were equal, there's a chance g is even. If they were odd, if they were opposites, there's a chance g is odd. These are not opposites, there's no way g is odd either. So right here, g is neither even nor odd. But a question for you. Let's say I found that g of negative 1 were also 3. Does that mean that g is an even function? If I show this, do I prove that g is an even function? Well, no. Because what about g of 0? Not g of 0 equals g of 0. What about g of 2? What about g of 3? What about g of 4? A single example like this could not prove that a function is even or odd, but a single counterexample can show that g is neither even nor odd. In a way, examples or counterexamples are more easily used to show that something is not true or that a neither case holds than to prove affirmatively that a function is, say, even or odd. Don't worry too much about this. All right. You can ignore the rest of this section, although it's kind of interesting. For example, an even function times an even function is even. An even function times an odd function is odd. It follows the rules of signed numbers. So for example, you can think of an even function as corresponding to a positive number. You can think of an odd function as corresponding to a negative number. A positive times a negative is a negative. And the proof, well, I talk about various proofs. I talk about a proof here in example 7. The proofs are based on that idea. So we can talk about patterns for products and quotients of even and odd functions. In particular, the reciprocal of an even function is even. The reciprocal of an odd function is odd. We're going to see this in trig. By the way, 1, which is a non-zero constant, this represents an even function. So these are special cases of even divided by even is even divided by odd is odd. because 1 represents an even function. In trig, we're going to say that the reciprocal of the sine function, namely the cosecant function, these are both odd, I should say. These are both odd. Sine and cosecant are both odd. Cosine and secant are both even. We're going to see that in trig. We can also talk about symmetry and equations. For example, the equation x squared plus y squared equals 9, the graph of that is a circle, and you can use various analyses to analyze various symmetries regarding this circle. Symmetries about the y-axis, x-axis, origin, and the line y equals x. Next up, speaking of things that don't pass the VLT, consider x as a function of y. Graphs, in these cases, they don't have to pass the VLT, but they do have to pass the what? The HLT. That's next time.